Hi everyone. I'm Tony, and I am a research scientist at Google. So today I want to talk to you about two recent works that my group at Google are working on, and we are basically working towards a goal, which is trying to create this math research assistant, and it's a sort of a research assistant, like like who you can talk to with your favorite math questions, or even solve the most difficult problems. So yeah, I guess it clearly has a lot of applications beyond just mathematics. And this is sort of the goal. And obviously, this is a non-trivial problem. So the question is, well, we've been working on this for like the last 6 years, and the question is, is there any new tools that we can use these days? Maybe this is pretty obvious to you guys, like large language models. So you have probably seen or maybe even played with ChatGPT these days, right? That's one of the large language models out there. These models can do lots of cool stuff. For example, writing like an essay on meaning of life. Like writing an email to a potential PhD advisor, or even design some like button. Just if you just describe in natural language, they're able to just directly give you the code, the implementation for it. So yeah, so these models are really, really impressive. And the cool thing is that behind all these very impressive capabilities, there's a very simple fundamental idea, which is this thing called language modeling. So I think I want to give you like a one way to think about why these models are super powerful, because language model, you can think of this as almost like a mixture of a diverse set of tasks. So what is language modeling? Let's take, for example, so first of all, like language modeling essentially is trying to model the distribution of text over the entire internet. This is what usually language model is trained on. So what this means is that, for example, if we just take any kind of math text on the internet, let's say just take one sentence, what we do is to actually predict the next token given a pretext, right? So for example, here, we're basically asking the model to say, like, for example, if you look at the last token here, given all the context, the theorem statement, and starting from proof if f p goes to q, then by lemma, now we ask the model to predict this token 3.12. So essentially, this is the language modeling task, which is predicting the next token. But in this particular context, you can see this is actually predicting which lemma to use. So essentially, the idea here is that, like, if you apply language modeling on the whole internet, on a large amount of text, that actually includes a large, various, diverse set of subtasks, even including lemma prediction. So this is why language modeling is such a powerful idea. Even though it's a very simple one, it can actually allow the model to do very impressive tasks. So, yeah, so what are these language models, right? Like, so they're like essentially also not just about this particular idea. The other aspect of this is the scale. The sort of if you just train a language model on like a very specific corpus, maybe it doesn't contain enough diverse set of tasks. But here we are saying that we're training on the huge data set, which is the whole internet, and also these models are also like hundreds of billions of parameters, and so these are the two types of two kinds of scaling that sort of enables these very impressive abilities of these language models. So yeah, so nowadays I think this is a very simple recipe if you want to do something very cool, which is scale up your model, scale up your data set, and if you have the money to train these models, then go ahead. So all right, so we thought about, okay, so basically can we do this for mathematics, right? So like, that's the question we asked, like how far we can go just by applying this simple recipe, like large model, large data set. So what we did for this Minerva work is we took the Google's largest model from last year. It's called IPAM. It's a 540 billion parameter model, and we then train on carefully processed internet metadata. So this would include all the archive papers, all the internet tokens that is written similarly to archive papers, like written in LaTeX, in MathJax, all of that. Yes?
Can you do tokenization differently than the way they do it in a general?
No. So that's a good question. I mean, the reason we didn't do it is because we took this pre-trained model, which contains the word embeddings of for the specific tokenization it was trained on. So obviously you can also replace that and retrain one, but we just thought, okay, let's just keep going and use the original knowledge that is learned on the large internet data set. Yeah.
When you say all of the archive, do you literally mean every single thing that's...
Yeah, up to, let's say, 2022 June, something. Oh, maybe not June, like probably January, yeah.
And when you say there are 540 billion parameters, what's a parameter?
Okay, yeah, so parameter here refers to a scalar, for example, let's say we have a matrix that does the linear transformation for one layer of neural net. And a matrix, like the number of parameters in there is just how many scalars in this matrix. Does that make sense? Like
the number of entries in the matrix.
Yeah, exactly, number of entries.
And so this is a deep neural network with that many matrix entries.
That's right, yeah. So that's how we get Minerva, essentially applying the same recipe, large model, large data set, and we got something that seems to be pretty good at imitating humans to do mathematics. So how well does it do, right? I mean, it's almost as good as a 16-year-old math student.
Good.
So it can solve high school mathematical exams. It got 65%. So first of all, one question here is that people often ask me is, if these models just memorize, some math exams on the internet. So to avoid these kind of, pollution or we took last year's newest math exam from Poland. Obviously, there could be still some kind of contamination happening, but this is sort of the best we can do. And we still get 65%, and the average is something like 57.
So average.
Yeah, it's above the average. And also we got something like 82% on the GCSE. This is a UK exam for 16-year-old.
You proved that UK is easier than Poland.
Well, that's high school math exam. So I think that's probably the university entry exam for high school students. So probably the level is different. Yeah. Right. So besides just attaining great scores, right? I mean, these models can also write out very coherent solutions with these reasoning steps. So this is the problem, right? I mean, it's simple to probably most of you. It's a very simple inequality problem. But the whole thing here is generated by the model. So again, this is a language model that spits out one token at a time. So the whole thing is just generated by this language model, one token at a time. But this really represents, this really sort of gives you like a very, coherent and a coherent solution with all the full details of how do you...
It gets to say square of a non-zero real number. Just
Exactly.
Uh-oh.
The detail is missing that A is not here.
0 points.
Okay.
Didn't use the hypothesis.
Yeah, that's right.
B is not equal to A, so there.
Yeah, but then you
No, but I'm
use the
saying-
hypothesis.
Yeah, that's right. Yeah.
It would take off 1 point.
Yeah. That's right. Yeah. So that's why we need human sort of feedback to.
You trained it on LaTeX, right? So
That's right.
it spits out LaTeX.
Yeah. Right. So there are like other. So first of all, like this. So the model was trained on all the archive papers, right? So it's not just mathematics papers. So We also evaluate this model on all the other sciences, like chemistry, physics. It got pretty good scores on these, like compared to the previous state of the art. Anyways, this is sort of the just story that tells you like how far you can go with this very simple recipe of scaling it up.
Wait, what does SOTA mean?
Oh, sorry, state of the art.
Okay.
Yeah. Sorry, that's
State of the art.
right.
The best.
So
Yeah, I know what state of the art is.
Yeah. Acronyms are very popular among computer scientists.
right. That's right. Yeah. Just to squeeze that in there. Okay.
Yeah, squeeze it in.
All right. Oops. What happens? All right. So. Okay. How can we go from here? Right. Where can we go from here? So I think one point I want to point out is that these language models, again, they're sort of modeling the distribution of text. So essentially, it's learning the concepts by the statistical correlation of surrounding words. But importantly, true meanings are not these kind of statistical correlations. They arrive from some kind of real experience or some kind of real grounding in the physical world. Or So. For example, here, like if I ask these language model, trying to complete this particular sentence, I am a blah blah blah, right? It predicts like 60% likelihood that I am a big fan of yours, but only very little amount of likelihood of I am a large language model. So the reason here is, again, just because this appears much more frequently on the internet. So this is like the reason why it will predict this with much higher likelihood. But again, so it's this kind of statistical prediction which does not really align with how humans think of the true understanding, the true meanings of these tokens.
Which part of the internet did it sample?
The whole internet.
The whole internet.
That's right. Yeah. Yeah. So we obviously
All of
apply.
Twitter, all of TikTok, all of Facebook.
Yes. So that's a very good question. We did definitely apply many filters to filter out some of the garbages on the internet. But we try to take as much as we can from the internet to train these models. So these models, yes, they will look at all the archive papers, Wikipedia, Stack Overflow, Meta Overflow, these kind of things. Yes.
So when you showed that you get the archive papers, wouldn't they already be in the language model?
No. So, I see what you're. So basically, you're saying the PAM, the original PAM model, right? Yeah. Very good question. So in PAM, we didn't actually process LaTeX properly, So there are two things actually. One is we didn't process LaTeX properly in the very first model, and also that was trained on the whole internet, so it doesn't have a very good specialization to these high technical content. So once we process LaTeX and also specialize into this mathematics content, the performance got much better. Yeah.
How does the specializing work?
So by specializing, I just mean that we only, taking this pre-trained model, we only then fine-tune this model or continue pre-train it on only mathematical text. So that's what I mean by specializing. Yeah. So for example, in the whole internet, maybe 1% of that is mathematics, and 99%.
That's too much. No, it can't possibly be 1%.
Yeah. All right, so I guess, I think just to give a bit more intuition about this, right? Like correlation is more like intuition, right? Like you can use the correlation to write a great poem about deep learning.
What in the world?
But they are very unreliable, right? So if you ask Dali to generate photographs of the stock market, they will generate bears and mans instead of actually understanding the true meanings of these bear stock markets. So basically, I'm trying to sort of connect to the autoformalization work, right? So basically, I'm trying to say that these models, even though they're really impressive, but they still need some kind of feedback, environment feedback, to ground these intuitions with real experience. So for example, if we take AlphaGo as one example, it was also trained on lots of Go plays, human Go plays, in the very beginning. But then what's important is they actually are also trained by playing games in the actual Go environment to receive, the kind of like feedback signals of winning or losing the game. So to actually experience this Go playing experience, to ground the sort of true understanding of what is the game, what is the rule of the game, right? And yeah, so I guess similarly, if we want to do this for mathematics, we want some kind of mathematical world for these kind of feedback signals. And luckily in mathematics, we do have this environment, which is the proof assistant. And I'm sure many of for the last 2 days, you have been hearing about this a lot. Essentially, this is some tool that allows you to go from this mathematical proof and tell you if the proof is right or wrong. Well, I mean, I guess it will tell you if it's the Go complete, if it's actually correct. With one caveat, right? I mean, the Minerva will output the natural language mathematics. And, like, the crucial bridge here is that, informal mathematics couldn't be understood by these proof assistants. What these proof assistants can understand is these formal mathematics, which are like mathematics written in these like programming languages. So to close the feedback loop, right, you actually want some kind of bridge to go from the informal natural language mathematics to formal mathematics. So yeah, so essentially like the whole idea why we are working on autoformalization, obviously autoformalization itself is very, very useful for verifying mathematics. But again, this also plays an important role to even improve our model's capability to do mathematics, to actually ground this model in this mathematical environment. So yeah, so that's sort of the basic story. But again, the problem now, the real problem is how do we, actually get this autoformalizer? And it was a very difficult problem. And in this talk, I'm gonna quickly go over like 2 papers that actually start to make a 0 to 1 progress in this problem. Like we actually start to see we are able to tackle this problem, starting from this paper from last May, which we show that we can actually autoformalize some statements to this paper. It was still put on archive last year, but yeah, it was accepted to this conference this year to autoformalize the entire natural language solution from into formal math proofs. All right, so yeah, so autoformalization, it's not an easy task. The task itself is extremely difficult. There are many missing information from the informal proofs, and you need to fill them out in the formal counterpart. And I'm sure many of the experts in the audience are much better known why this is difficult. And also, from a machine learning point of view, like for me, if I want to train these models, ideally we have some data sets to train these models to do autoformalization. But on the internet, it's very hard to find such aligned pairs of natural language to a formal language. So yeah, we lack these kind of data sets to train machine learning models. So yeah, so I guess it's been like we've been working on this problem for like the last 4 or 5 years, and there have been multiple works like unsupervised machine translation, etc. But it still doesn't really work on this problem. So we kind of hit a bottleneck until we find, hey, what if language models are so powerful and maybe they can do something for us too, for autoformalization. So yeah, so starting from this, essentially last year, we basically started to play with language model to do autoformalization. And so one thing that you start to play with language model, you need to learn about this thing called few-shot prompting or in-context learning. So these are the same thing with just 2 different names. Essentially, few-shot prompting means that you show language model some examples, a few examples in the prompt before you provide the actual problem. So here, basically, what I'm showing you here is that these are the 2 examples I showed to the language model as like this is an example, and then maybe you should just learn from these examples. And it's specifically, I'm showing one natural language sentence followed by an Isabel translation of that. And there are 2 of them in the prompt. So now after this, I'm going to say natural language version, blah, 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 and then please translate that into Isabel. So that's called like, so this is essentially like, this is the few shot, and the whole thing called few shot prompt, and this is, the technique is called few shot prompting. So I guess essentially this prompt, I just, I randomly just cook up these 2 examples. There are still some mistakes in the prompt that people found out later. But essentially, like with just one first try, I tried on this problem. That is, prove that there is no function f from the set of non-negative integers into itself, such that f of n equal to n plus 1987 for every n. So
we had this question.
Yeah, we both sat that exam.
Oh, okay. Nice. Yeah.
Me too.
Oh yes, I'm Jordan.
Yeah, so we ask basically Codex, which is a language model, to with the prompt that I showed, to auto-formalize this problem into Isabel. And it was very surprising to me that it directly translates into a perfect translation in Isabel. Again, this is really just my first try. Like it's pretty amazing that these models just really shocked me at the time. And here, for example, I think the real interesting part here is that there are two points I want to make. One is, the model needs to understand the notion of there is no function f. So to deal with this, the model basically assumes there exists such a function, and then it shows, this is a contradiction. That's how it formalized this. And also, it needs to understand, the natural language, like what does it mean by into itself. So the non-negative integers into itself, and then it actually correctly translates into natural to natural. So yeah, it definitely demonstrates a very impressive capability of understanding natural language and also being able to, translate into correctly, translate to Isabel correctly. That's the first example. The second example is even more surprising to me. This example is pretty simple, right? It's a grade school math problem. It says when all the girls at school line up in rows of 8, there are 7 left over. And instead, if they lines up in rows of 4, how many are left over? The final answer is 3. So this kind of problem wouldn't be interested to formal mathematician at all, I assume. I think the point I'm trying to make here is that this is quite of a what we call out of distribution problem for formal mathematician. Like you don't see this kind of problem on the internet, but still the model is able to somehow correctly translate this natural language problem into a Isabel formalization. So this is quite surprising to
Was this after you trained it on archive or before you trained it on archive?
No, this is actually just so this Codex model is not the previous Minerva model, and this is trained on just code.
Okay.
Yeah, but supposedly it may also be trained on archive. Yeah.
It says
So it was.
Oh, sorry. Yeah, this model. Sorry. Okay, I forgot. The last one is Codex. This one is PAM. Yeah. So PAM is trained on archive. Sorry, it was trained on. It was not trained on archive. Yes, that's right. Yeah. So yeah.
You did not specialize it to Isabel.
No.
So it just got Isabel from the internet
Yeah.
before.
Yes, that's right. Yes.
And was this trained on just 2 examples, as you said before, TwoShot Training?
Right. So TwoShot. This is just putting these examples in the prompt without actually changing the weights.
I see. Okay.
Yeah. Yes.
But for instance, there are syntactic elements in your answer which are not present in your two-shot training, like the / right arrow. So does that mean, is that coming from
the internet?
Isabel stuff that was in its training
Exactly.
set?
Yeah.
Okay, so it's able to sort of context locate and be like, oh, this looks like
Yeah, exactly. So basically, that's the right way to think about this few shot prompt. Essentially, it's not like actually learning from this few shot prompt to come up with all the Isabel translation. It sort of puts you into the right, formatting. The model starts to generate Isabel code.
So it wouldn't have worked if there hadn't been Isabel code in the training.
Yeah. So Isabel. So Isabel does. There's definitely Isabel on the internet.
Right.
But my point is that, first of all, I'm not sure about these examples. Maybe these examples could appear, but I think still very unlikely. But definitely not this example. This example definitely wouldn't appear on the Isabel on the internet. That's why this is pretty amazing to me. Yes.
Your slides back on those your two-shot thing. Does it not have an issue with the fact that I means two different things in the first example? Does that not freak it out?
Which I?
I is an index, and it's also a complex number.
I see.
No, it understands boundary variables.
It gets that.
Yeah. Oh, so first of all, this example I wrote myself. So I guess I think it does. It is able to understand I differently, but okay. So this example is. I mean, there are actually some mistakes here as well. Like, so it shouldn't take the. Again, these models are not actually learning from the examples. So there may even be mistakes in the prompt, but still the model is able to understand what the problem is. Essentially, this is almost like, okay, well, can I infer the problem from the prompt instead of actually learning how to translate? Does that make sense? Yeah.
The sums I equal 1 to 1.
12. It's LaTeX.
Yeah, it's LaTeX. It's LaTeX issue. Yeah. So there are some prompt mistakes in this.
The 2 belongs up in the.
Yeah.
Just curly braces.
Yeah, that's right. Yeah.
Oh my goodness.
Yeah, I think I forgot to use the bracket over there. Anyway. All right, so let's look at a failure case, right? What these models couldn't do. So for this problem, we asked the model to formalize this notion of a linear function. Let f be a linear function for which f of 6 minus f of 2 equal to 12. What is f of 12 minus f of 2? The final answer is 30. So the model, interestingly, just says assume linear f. And the linear f doesn't exist in Isabel. So essentially, it made up a name called linear f without actually without knowing that linear f doesn't exist in the Isabel library.
This is indication that it should exist.
Yeah.
Yeah, right. So it should. But the cool thing is that if you show one example in the prompt, so instead of like showing these two examples that I showed you earlier, if you show one example that tells it how to sort of formalize the notion of a line. Well, here is even the line is not a linear function. So even if you tell it, like this, if you show this example in the prompt, then the model suddenly knows how to formalize the notion of a linear function. So again, the model does pick up some notion of how to formalize some particular notion in the prompt. Yeah, so that's pretty cool. So this is essentially like it shows the importance of like you need to show good examples in a prompt in order for the model to understand how to translate. Right. Okay. Right. So main takeaways: language models can formalize to some extent, despite there is a little amount of data in the pre-training corpus. For Isabel, it's only very little. It is even capable of completely out of the domain problems, like the grade school math problems. And also, we can teach the model to do better just by showing relevant examples in the prompt. And we did a couple more study on the sort of more qualitative evaluations. Like we took like 240 problems in total, and essentially, blue score is a metric. The higher, the better. It's a metric of like measuring how similar it is from the translated sentence to the ground truth or the correct sentences. And one trend that is obvious to us is that if you scale up the size of the model, then the performance gets better, which is, again, sort of following the simple recipe that I was telling you about, like scaling it up. And also, we did a bit more human study of like where the mistakes are. So I think the interest. So first of all, like it's not perfect. It only can translate perfectly 38 out of 150 problems from this data set. So math problems is essentially a list. It's a data set of high school competition problems So it's only able to translate like about 25% of them. Yes?
But we are still talking about the statements only, right?
Yes, so this is only a statement. So this is only about translating a statement. And we have a human to actually label if the statement is translated correctly or not. And we find that most of the mistakes come from like misalignment of the definitions, like the linear F that was shown earlier. So that's sort of the rough idea. So that's sort of the rough first work. We show that the model is able to do something like this. In this paper, we show a couple more things, like using this autoformalization tool to improve our theorem provers, including like also just do the opposite, which is not autoformalizing but informalizing. Like so going from formal language back to natural language. So that's also very interesting, right? I mean, because for me, I'm not like an expert in formal systems, and when I read these things, it look kind of obscure to me what they mean. But if I ask codecs to translate that into natural language, this is much better, much easier for me to understand. And importantly, you see this particular example here. Like in the Isabelle language, it is spit out pretty very low level. Like you have to say X is in A, then X is in B. But in the natural language setting, the model just directly say A is a subset of B. Which is pretty cool. Similarly here, like again, this is a pretty like uninterpretable statements in Isabelle. But if you ask the model to translate into natural language, it's very clean, it's understandable. So it's a pretty useful tool, and also potentially it's good for getting more training data for doing the opposite direction. That's what we call as the back translation.
Is the accuracy tied to sort of how close or how similar the output is to existing?
Yeah.
If you
potentially yes. Yes.
If you took a very artificial but correct statement, it would not do a natural language translation as well.
Artificial, I think so. There are a lot of lemmas in these formal libraries that don't really appear in natural language, and we did this informalization for these as well. And some of them do look reasonable. So I think it's not just that they can only formalize or informalize those statements that appear on the internet.
But Patrick had a very...
we made experiment last summer with this exact codex thing, and we tried just like stating stuff about derivatives, but using a slightly non-standard definition of derivative, but still correct. And clearly the model was just spitting out Wikipedia's definition of derivative, completely disregarding what was actually the formal statement.
Yeah.
Does prompt engineering work here? For example, for the problem with linear F, for example, what if you in the prompt ask something like defining each term from scratch, for example, or something that sort of forces it to?
Yeah. I think if you try ChatGPT, I tried it this morning. It actually gives you the whole definition of linear F and etc. So yeah, I think prompt engineering definitely can help there. Yeah. Yes.
You said before the formula about formalization, and this is about the formalization.
Right.
And you again fine tune with the data with opposite side.
No, we haven't done any fine-tuning in this work. But I think that's a very good idea. So like basically, if you can, do this informalization, and you can now obtain this pair, so that you can do fine-tuning on this pair, right, for the other direction. Yeah. So that's called back translation. Yeah. Yes.
Have you done this with like auto-encoding? So you start with the one version, translate Isabelle, and translate back, and it gives you a way to sort of train the model.
Right. So these are like very, I think, so this sort of belongs to the unsupervised machine translation type of like works in the past. And people have done a lot of things like that, like auto-encoding or like denoised autoencoder and these kind of things. We haven't tried that. I think it's a very interesting direction too. Yeah. All right. So how long do I have? Okay. 15 minutes, right? Okay. Cool. So, all right. So yeah, the next line of work is going beyond just the statements. To show you these models can even do translation of proofs. And that's pretty surprising, right? I mean, natural language proof is pretty high level, formal proof is low level, how do we expect this kind of, I wouldn't say one-to-one correspondence, but like some kind of like, direct translation of that, right? So the key idea here is that we don't translate the natural language proof into the whole formal proof, but we translate the proof into a formal sketch. So the formal sketch is, instead of a proof, it means it's a list of formal conjectures so that we can fill it out in the formal math library. So the whole thing is, we call it draft, sketch, and proof. So basically in the setting, we are given like informal statement and a formal statement. And we first ask some kind of informal proof writer to draft the informal proof. So this could be a human or could be a machine, like a language model like Minerva, to spit out this informal proof. And then the ingenious thing here is that we translate the informal proof not directly to a formal proof here, but we first translate into a formal sketch. And here you can see that, for example, the sketch essentially is a list of formal statements which correspond to each of the steps in the informal proof. And then the third step is to prove each of the formal conjecture using some off-the-shelf prover in this formal system. And so that eventually this whole proof gets verified in a formal system.
In the displayed example, there's some information loss, right? I mean, like the informal proof had a hint, which was dropped by the time, like the first rectangle in the informal proof suggested a tool to prove that conclusion, and then when you put a formal sketch, the tool was omitted, right?
You mean we know this sentence, or yeah. So that's right. So not everything in the informal proof got fully translated into the formal proof, but sort of here we just in this case, this seems like this hint is not even needed to close this formal conjecture. Like the off-the-shelf prover is able to prove that statement directly.
That's the.
Oh, right. Sorry. Yeah, that's right. Using assume. Yeah, that's right.
No, it uses the lemma that the GCD times the LCM.
Yeah. GCD. Oh, yeah, that's right. Yeah. So the point here is that like this thing here was directly. This is generated by this prover.
So what is that prover?
The prover here is a sledgehammer in Isabelle. If you know sledgehammer.
So you are calling sledgehammer all the time, right?
Right. So basically now once we have this list of formal conjectures, we just directly call sledgehammer to prove each one of them. So the sledgehammer doesn't have that hint, right? It basically finds the proof for that automatically. Right. So for this particular statement here, yes, I guess for all the three statements here, this was completed by sledgehammer.
But like if you gave sledgehammer the original formal statement, would it be?
No. So yeah. Oh, sorry. The original formal statement is in there. But then you basically goes into this, declarative proof style where you start to prove this little proof in this proof block.
The question is, can it do it all at once?
Yeah, if you just feed the formal statement directly.
You feed directly to ask the sledgehammer to prove that. Yeah. No, you cannot. Yeah. But we do have some. So in the paper, we will show you like how many problems does sledgehammer prove? How many proofs can we prove using this? How many proofs using other kind of techniques? Yeah. Right. So I guess I think I could just skip those. Essentially, maybe one more detail here is that the formal sketch is essentially just doing. How do we get the formal sketch? We're just doing some kind of prompt engineering. And interestingly, we don't need to actually translate each one by one. We just directly output the whole formal sketch in one run. So using some specifically designed prompt that we made up. And here, I guess here we use sledgehammer for the off-the-shelf prover. Like essentially for each of the formal conjecture, we apply the sledgehammer, and so they close each of the little conjecture, and then they close the whole proof. Okay, so just to show some results, we have, so in our community, we have this sort of standard benchmark called mini F2F. These are like 488 problems. These are like high school mathematician problems, high school competition problems. And they could range from AME, AMC, or even some of them are IMO problems. But like most of them are easier than IMO. So in total, there are like 488 problems stated in formal language. So essentially, if you use, so if you think about the thing that I showed you before, you have the first step, writing the informal proof. And in this case, we just take the human informal proof, and then we try to auto-formalize that human informal proof into a formal proof to prove that statement. And in this case, we know for sure the informal proof, the natural language proof is correct because it's generated, it's produced by a human. Okay, so we make sure that the human. Yeah. So it's generated by actual we script the solutions from the internet, like the solutions.
Must be fine.
Okay.
You're just digging yourself deeper, right?
Yeah. It's a website that contains all these high school competition problems with problems and solutions. Yes?
Yeah, I hope that that PAM did not scrape from Fixera.org.
Yes. It's possible that PAM or Minerva scraped those too. So I'm not like so for this we don't claim that the Minerva or like PAM memorizes these problems or not. Yeah. So, but again, in this case, we use these like script human solutions to do the auto-formalization, and for each of the human solution, we auto-formalize this many times, like starting from 1 to 100. So this is how many problems as you give more tryouts of the auto-formalization, and yeah, eventually with 100 tries, you are able to auto-formalize or prove 200 problems out of this 488 problems. I guess showing you these numbers may not be very, very concrete, but I will show some examples later. But interestingly, if you just use like Minerva instead of human to prove them, it's actually getting about the same. It's able to first use Minerva to generate informal solution, and then we ask the codecs to translate these informal solutions generated by the Minerva into formal proof.
Into Isabel.
Into Isabel, yes, exactly. And that was able to prove 199 problems, which is pretty cool. So here, maybe one way to think about this, why this is actually pretty good, is that like human solution, there's only one, right? But here we ask Minerva to generate also 100 of them for the same problem, and we translate each of the problem into this formal proof once. So in total, there's like also 100 proofs, but we do potentially benefit from the diversity or diverse set of potential solutions generated by Minerva. So Minerva was able to generate more than just one human ground truth proof. So some proofs are more easier to be formalized, and some proofs are harder. And this is why we believe like Minerva was able to solve about the same problem. Yeah. Mm-hmm.
Did you find that there were actually, I mean, of course, this doesn't have a mathematical definition, but did you find that different proofs were found for the same problem?
Yes. So different, well, I guess by different, I mean, more like, question, right? I mean, yeah, words, like they're like different. I have a look into.
I don't mean word for word the same, but I mean, there are questions which have two problems that we humans looking at them would consider
I
different.
didn't look into actual, whether the models produce two different strategies to prove the same thing. Yeah.
So were these trials, are they just completely independent trials with no memory or feedback from the previous ones?
Correct.
Then you should get an exponential curve. You shouldn't get any other curve. Wait, so like when you say 100 trials, you just try 100 different.
Right. So there are some problems that, regardless how many times you try, you still don't get one auto-formalization correct, right? So there's going to be some kind of saturation happening. Like, yeah. So there are some easier problems that you can get with only little amount of problem.
Okay. No,
Yeah,
I-
yeah,
okay.
yeah.
There's a different exponential curve in a different dimension. I get. Yeah, I get
Right,
that.
right. Oh, yes.
So there's 200 problems and 199 problems.
Yeah.
What's the intersection? Are they the
Yes.
same problems?
Yes, good question. So they're not the same problem. So in total, they solve 214.
Oh, they're
Okay.
nearly the same.
Almost the same.
So almost the same, but they're like, I think 15 problems that are different. Yeah, I guess. Yeah,
And did you check if any of the IMO problems were part of those 214?
I will show you. Yeah. So I guess like, so we've been working on this for a while. So this benchmark, like, I just want to show you like, this is what I just showed you, like the numbers in terms of percentage. And it's important to see that just by this is whole just few shot prompting without any specific fine tuning whatsoever, is actually better than all the previous methods that we have done before. So this is quite impressive to us. If for those ones that we actually work on this benchmark, this results are actually pretty amazing. All right, so yeah, so that's exactly the question you asked. Oh, sorry.
You had a comparison of Sledgehammer. This is Sledgehammer directly on the problem.
Yeah, exactly.
by itself.
Yeah, exactly. If you apply Sledgehammer directly to the statements, you get to this level. Sledgehammer plus some heuristics, plus some using assumes, using these kind of things, then it gets to something like 18, 20. That's the kind of level, yeah. All right, so just show you some examples. As one, you asked, right, whether there's intersection, or actually this actually lives in, this only can be solved by Minerva, but the human solution couldn't be auto-formalized, like. So this is one example, like that's solved by Minerva.
So just let me get this clear. This informal proof.
Yes.
What was Minerva given? Just the statement.
Yes, exactly.
You didn't give it any more hints at all.
No.
You give it the statement. You say, please generate a natural language proof.
That's right. Yeah. With a few
And it
examples.
says, oh, this is an old IMO problem. I've seen 10 proofs of this on the internet. I mean, it might say that.
Yes. So this could, of course, this could just appear on the internet.
Yeah.
I'm not claiming that this is something that the model generates by itself or novel, but yeah. Sorry. Yep. Mm-hmm.
Before the page, can I ask the size after that? Yeah, the size of Thor and what's that?
The Thor?
They use the large language model.
No, they don't use a large language model. Mm-hmm. So we're not doing prompting or whatsoever for these two methods. We're just like doing, use like it's still transformer, but it's a smaller transformer fine-tuned on Isabelle to do theorem proving for Isabelle. Yeah. So it's much more specialized to Isabelle proofs than this large language model, which we haven't really fine-tuned them on Isabelle, but it's on the internet. Yeah. So for this example, like the Minerva actually is able to, produce the solution and also auto-formalize the proof and checked in the Isabelle. So that's pretty cool. Another very cool example I want to show you is this a very long proof. It's a very simple problem. Like it's the same as like if x minus 1, the absolute value of that plus the absolute value of x plus blah 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 is x plus 2. Then you want to show this x lives in this interval. And in natural language math proofs, you have 3 cases. So it's by case analysis, right? You analyze if x is less than minus 1, or it's in between, or it's larger than 1, and then you show that the only possible values for x is only in this interval.
So who wrote that proof? That human?
I believe a human wrote this proof, yeah.
Pretty bad latex.
I see. Yeah. All right. So it turned out that the model actually was able to auto-formalize the whole thing, and for each of the case, it actually formalized the whole proof block for it. So this is the first. This is the first case, which is when x is less than minus 1. It auto-formalized the whole thing here. It will try to put each of the steps into the formal conjectures, and then it's closed by Sledgehammer. And then the second block, the third block. So it's a super long proof if you actually look at it. But eventually it concludes that the thing is proved as a result. The statement is proved as a result. Yeah. So anyway, so that's sort of like all the cool stuff that I want to show you guys today. Oops. Yeah. Okay. So. Okay. Yeah. I guess. Okay. So maybe one more slide just to reiterate on the sort of the sort of the thesis that we want to combine the sort of the two lens of mathematics. One is natural language mathematics and formal mathematics via autoformalization, so that we get grounding and also lots of data from the internet. And I guess, okay, so then I want to say something about where do we go from here. Like I've been working on this since like, these two works. I'm still working on it now. And these systems, even though they look pretty cool and already pretty impressive, but it's still not very reliably. Like so basically, it's still not very reliable. I think autoformalization. Probably the number one problem is that autoformalization of a statement. This problem cannot be verified automatically. Like, how do you know if this aligns or not, right? I mean, there's no automatic tool to check it. So it's hard to actually gather like feedback signals to improve the model. So ideally, we want to have some kind of human signals, human feedbacks to tell the model, hey, you're making a mistake. And also, as I said, I mean, as I shown earlier, there's this misalignment of the definitions. The model doesn't know which definitions appear in Isabelle. And we have been working on like retrieval augmented models so that, so this means that the model, instead of like just memorize these names, it actually is able to do some kind of retrieval from like a large database to retrieve the correct name or definitions. So there are some works that we were working on, like memorizing transformers or some kind of other kind of work that's called retro. So this is more machine learning kind of improvements that we are making. And also like, I think prompt engineering is also always very helpful. Like you show that, you see that, showing one relevant examples actually can allow the model be able to autoformalize new examples. So ideally, we also want some kind of better prompts or better examples. And one problem I don't know how to even tackle is how do we formalize definitions? So that's, it's probably the most difficult part of formalization in general, like how do you set up the data structure of the whole library? And then there's also the problem of how do we evaluate such system? We don't even have a data set, not for training nor for evaluation. So I want to highlight that these kind of three things would require more human support. So I was trying to see, can we get some community support to help us to improve this autoformalization system? So I think I'm very happy to be here so that I can talk to the math community about this work that we are pushing for. But also, I would love to see, to see if we can actually gather some community support for these kind of things that actually require more human feedbacks. Lastly, there's one very concrete proposal that I have in mind. I talked to some of you about it. Whether we can collect, let's say, 5,000 to 10,000 statements from university level textbooks. What we do is we've auto-formalized them using language models. But then the important thing is that we want humans to annotate the sort of the translation, whether it's correct, what kind of mistakes it's making. If we have such a data, then we have two things that's achieved. One is we actually get a benchmark for auto-formalization or like trying to prove university level problems, but also a training data set for to provide more supervision to formalizing those statements so that the model can actually get improved in auto-formalization. But yeah, I think these are just my 2 cents. I'm not sure how feasible or realistic this is, but any feedbacks are welcome. Yeah. All right, that's my talk. Yes.